Hi again, everyone. Part 2, the speed of EMR. So, of course, this is talking about how we figured out that the speed of light was 3.00 times 10 to the 8th meters per second. So, we know this, we've alluded to this, we've talked about this before, it's on your formula sheet. Okay, so this is just basically how they did it. Okay, so I'll give you a little bit of history. So, Galileo was the first one to try to determine the speed of light. He and an assistant stood about 1 kilometer apart, and each had a covered lantern. Okay, one would uncover their lantern, and then the other would do so once they saw the first one. Galileo used his pulse to measure the time from when he uncovered his lantern to when he saw the other lantern's light. Okay, now obviously not very accurate. Just bad, but at least they tried. Okay, in around the mid-1600s, okay, Roemer and Huygens used the moon of Io, okay, that's the brightest moon of Jupiter, to calculate the speed of light as its orbital period of revolution had been previously determined. Io was seen to be eclipsed by Jupiter later when Earth was further away from Jupiter than when Earth was closer. He used this change in distance, basically Earth's orbital diameter, and the change in time to determine the speed. Okay? So let me just draw this because I know lots of you are already like, what? Okay, so here's the sun. Here's Earth rotating around the sun. Okay, and Jupiter is like way out here. So basically, Jupiter's here, it's got this moon. Okay, so the moon, Io, would move around Jupiter and it would be eclipsed. So as it moves behind Jupiter, you can't see it anymore, and then, of course, it moves back around so that you can. So when Earth is close to Jupiter, or closer to Jupiter, okay, so you look at Io, okay, and then 6 months later, when Earth is on the other side, okay, they look at Io again, and of course, Jupiter has a really huge orbit, so it doesn't move very much in 6 months. Anyways, what they did is they figured out that this distance, and they knew, don't ask me how, but they knew Earth's approximate diameter, or the orbit of the diameter of Earth's orbit around the sun, sorry. Okay, so they had a good estimation of that distance, and they figured that the difference between the time it took to see Io in the close approach versus the far approach, they figured that out to be about 22 minutes. Okay? Or 22 minutes late. So the idea was they knew that distance, they knew that time, and of course velocity is simply distance over time. So they converted all that, and they ended up with this calculation of 2.3 times 10 to the 8th meters per second. And if you look at this next comment, that's actually not a terrible measurement considering the equipment that they used. Like that's incredible, really, incredibly close. Because again, the orbital distance was an estimation. They didn't have great instruments for measuring time, and this was mid-1600s. Okay, 1700. Like this is incredible. So yeah, good for them. Okay, then we have this guy named Fizeau. Okay, in 1848, he used a rotating tooth mirror with an intense light source, lenses, and another mirror. Okay, tooth wheel, intense light source, lenses, and a mirror. The light went through the gap in the tooth wheel as it rotated, and it then traveled 8.63 kilometers to a large mirror and then reflected back. Fizeau measured the time it took for this trip and used it to find the speed of light to be 3.15 times 10 to the 8th meters per second. Okay, he was also the first to examine how light travels in different mediums, and he did a similar experiment in water. His experiment there concluded that light is actually slower in water than it is in air. So that's going to be important for refraction later on. Okay, now, so there's some of the history about the speed of light. Now let's get into kind of some current stuff. And current is still over 100 years ago, but still, don't focus on that too much. So let's look at Michelson's experiment. So Michelson took Fizeau's idea, okay, and then modified it slightly. He used, instead of a toothed wheel, he used an 8-sided set of rotating mirrors. Okay, he used the frequency of rotations. Now that, of course, is measured in RPSs, rotations per second, so that's frequency. Okay, and the distance to the curved lens and back, curved mirror and back to determine his calculation. The key was getting the exact frequency so that the light would hit the next mirror and be observed. So basically what has to happen, okay, so this light comes in, okay, gets reflected off this plane, okay, goes back or out to this curved mirror, okay, like 35 kilometers away, bounces back, and in that time, this, here I should write in red, okay, this mirror, that side, would have moved to right here, okay, so exactly 1/8 of a turn. Okay, of course, if it's slightly off, then what happens is that light doesn't get reflected into the telescope, it gets reflected elsewhere and you can't see it. So what he did is he sped up or slowed down the mirror to make sure that you could see the reflection in the telescope. Okay, so that's kind of his idea, his plan. Now what happens is in all questions like this, we assume that it's going to be a 1/8 turn of the mirror. Okay, now of course you start at 0 and you speed up until you can see the light. Well, that's 1/8 of a turn then. Okay, if you speed it up even more, you might be able to get 2/8 of a turn. Okay, now there is one question in the set, I think, that says 2/8 or 2/6 or whatever. They have to tell you if they are expecting more than one fraction of the turn. They have to tell you that. If they don't, you just assume that it's 1/8 or 1/6 or 1/12, just whatever it is. Okay, not a big deal. The other thing that we have to know is that light does not accelerate. Okay, it is just the speed it is the whole time. Okay, so remember, c is really just a velocity. So remember, velocity is distance over time. So of course they just use c is distance over time. Okay, so that's the idea. Here, in this case, in Michelson's case, the distance was 70 kilometers, 35 there and 35 back, so 70 kilometers total. Okay, the time can be determined using a ratio. We'll talk about that in a minute. Okay, and again, unless otherwise stated, we assume that the mirror rotates only one face. So 1/8 for an 8-sided mirror, 1/6 for a 6-sided mirror. Okay, so if an 8-sided mirror spins at a frequency of 533 hertz and the light travels 70 kilometers round trip, then we can do this basic calculation here. So 533 hertz means 533 rotations in 1 second. So we just set up a ratio, 533 rotations in 1 second. So that's that side. Okay, and then we figure out, okay, well, we have 1/8 of a rotation, right? 8-sided mirror, unless we're otherwise told, it only goes one face, so 1/8 of a rotation in t amount of time. And we simply cross multiply and divide to get a time of 2.35 times 10 to the negative 4 seconds. Okay, now in his experiment, remember it went 70 kilometers, so that's 70,000 meters. Okay, and 2.35 times 10 to the negative 4 seconds. Of course, you divide those, and he ended up with a velocity of 2.98 times 10 to the 8 meters per second. It's extremely, extremely close. Okay, and then as we refined that experiment and tried it some more and got better with the frequency and the rate of spin and all that, that's how we came to our accepted value currently today of 3.00 times 10 to the 8th meters per second, which of course, again, is on your formula sheet. So that's what we use now. But Michelson's very first one was 2.98, so extremely close. So awesome. Okay, so let's do some examples and get you guys on your way. Okay, students using a 12-sided set of rotating mirrors in an experiment similar to Michelson's determined the speed of light to be 2.88 times 10 to the 8th meters per second. The mirrors are located 30 kilometers from the fixed mirror. What is the frequency of rotation if 1/12 of a rotation occurs before the light returns? Oh, okay, so this is kind of backwards. So instead of finding the speed of light, okay, they gave us this speed of light from their experiment, and they want us to figure out how fast the mirror is spinning. Okay, so really what we need to do is we need to figure out time. So we are given the distance, 30 kilometers. Okay, now that is to the fixed mirror, so we have to go 30 kilometers back. So we have a 60 kilometer return trip, which of course is 60,000 meters. Okay, awesome. Okay, and then we know that distance is velocity times time, so then time really is just distance divided by velocity. So that is 60,000 meters divided by 2.88 times 10 to the 8th meters per second. So these students are figuring out a time of 2.08 times 10 to the negative 4 seconds. Awesome. Okay, so now we just set up that ratio. So we want to know how many rotations per second. So I guess we can call that X. It's a frequency of rotation, so we can still call it an F if we want. So F over 1 second, okay, is equal to 1/12 of a rotation in 2.08 times 10 to the negative 4 seconds. Okay, and again, we cross multiply and divide. So 1 times 1/12 divided by 2.08 times 10 to the negative 4, and that works out to 400 rotations, okay, in 1 second. Per second, well, of course, rotations per second, that's what a hertz is. So this is 400 hertz. Number 2, light reflected from an 8-sided set of rotating mirrors travels 15.0 kilometers to a distant fixed mirror and then back. At what frequency is the set rotating if it is turned 1/8 of a rotation before the light returns? Okay, so this one's very similar to number 1. Okay, the idea is, okay, so we go 15 kilometers there and then 15 back, so we have a total distance of 30.0 kilometers. Okay, awesome. Okay, and so yeah, we do the same thing. So time is distance divided by velocity. Okay, so our distance, so 30 kilometers is 30,000 meters divided by, this time we didn't figure out an experimental value for the speed of light, so we're just allowed to use 3.00 times 10 to the 8th meters per second. Okay, so that yields us a time of 1.00 times 10 to the negative 4th seconds. Okay, so once we have that, we'll do the same thing as before. We have, if we want the frequency, or the frequency is per 1 second, or the number of rotations. Okay, and we have to go 1/8 of a rotation in the 1.00 times 10 to the negative 4 seconds. Okay, we cross multiply and divide, and that gives us 1,250, so 1.25 times 10 to the 3 rotations in 1 second. Well, remember the rotations in 1 second is a hertz, so that's 1.25 times 10 to the 3 hertz. So these set of mirrors are spinning 1,250 times every second. So that's pretty fast, but, well, go with it because that's how fast these things go. Okay, then number 3, an 8-sided set of mirrors, similar to Michelson's, rotating with a frequency of 500 hertz, is located 36.0 kilometers away from a fixed mirror. If the returning light is observed in the system, at what speed is the light traveling? Okay, so this doesn't tell us that it's rotating more than necessary, so we are going to rotate 1/8 of a turn. Okay, so we know that it's spinning at 500 rotations every second, every 1 second. So if it goes 1/8 of a rotation, okay, we want to know how much time that takes. So cross multiplying and dividing, okay, that works out to 2.50 times 10 to the negative 4 seconds. Okay, great. So remember 3 sig digs, because the 1/8 is a perfect fraction. Okay, so it doesn't figure into sig digs. The 1 second here, that's part of the Hertz unit, so that's also perfect. So the only thing we're measuring for sig digs is the 500. So that's where the 3 sig digs come from. Okay, and then of course remember, distance is velocity times time. So we want the velocity, so that's distance divided by time. So we're going 36 kilometers there, okay, hitting the mirror and coming back. So 36 there, 36 back, so that's 72 kilometers. Okay, 72.0 I guess. So that's 72,000 meters divided by 2.50 times 10 to the negative 4th seconds. Okay, and then that works out to 2.88 times 10 to the 8th meters per second. Awesome. So that's that, guys. I would like you to practice this section, page 652 in your textbook, numbers 4 to 11. And that's a lot of questions, so really if you just choose 4 of them, that would be plenty to get these ideas in. All right, again, you can use your textbook, or you can print this from the card, from the workspace card in the workspace. Anyways, thanks guys. See you next section.